This video is another in the series from Math 1224 for UTSA. Today we're talking about Chapter 6, Power Series. Section 6.1 is on power series and functions. So, a function of the form f of x equals x to the n power is called a power function because you say x to the n power and can be any real number. Typically we'll use a whole number though in this case. Any series with this form is called a power series centered at 0. So c sub n times x to the n power. So c0 would be the constant term or constant coefficient, c1 would be the linear coefficient, c2 would be the quadratic coefficient, and so forth. A series with this form is called a power series centered at a. A could be 1, 2, 3, or whatever, pi, e, any real number really. And then the cn's are the coefficients. So let's look at an example of that. So if I have the series as n goes from 0 to infinity of x to the n over n factorial, what would that look like? So we'd have x to the 0 power over 0 factorial plus x to the first power over 1 factorial plus x to the second power over 2 factorial plus x to the third power over 3 factorial, and so on. Now x to the 0 power is going to be 1, right? Because of the exponent. We have an empty product. So, well, likewise, 0 factorial is also 1 because you have an empty product. You have a product of no things, essentially. It's one way to look at it. So that first term is 1 over 1, so it's just 1. So 1 plus x squared over 2 plus x cubed over 6 plus ... The next term would be x to the fourth over 24. So that's our series. So we can look at, well, when does this converge? So for example, if x equals 0, because that's the center, right? We don't have a x minus 1 to the n, we just have x to the n. So 0 is the center in this case. If x is 0, well, then we would just have 1 plus 0 plus 0 over 2, which is 0, plus 0 over 6, which is 0, plus a bunch of zeros. We would just have 1. So if x is 0, this converges to 1. Okay. What if x is not 0? What if x is, say, 1? Right? Well, then this would be the series as n goes from 0 to infinity of 1 to the n power over n factorial. And 1 to the n power is always just 1, so this is the series as n goes from 0 to infinity of 1 over n factorial. Now, does this converge? And this is one we probably showed earlier, but we'll do it again. Let's use the ratio test for this one. So rho equals the absolute value of 1 over n plus 1 factorial over 1 over n factorial. Okay. Oh, I forgot something. Of course, the rho is the limit of this as n goes to infinity. Okay. So this is the limit as n goes to infinity of the absolute value of 1 over n factorial, n plus 1 factorial, times n factorial over 1. Okay, now I'm going to rewrite n plus 1 factorial as n plus 1 times n factorial. So this is the limit. And also, while I'm at it, I'll combine the two fractions into 1. And while I'm at it, let's drop the absolute value bars because everything's positive anyway. So this is n factorial over n plus 1 times n factorial. So I get some cancellation here. So this is equal to the limit as n goes to infinity of 1 over n plus 1, which is 0. So we get absolute convergence. Okay. So if x is 1, we get absolute convergence. What if x is 2 or 3 or 10? Well, let's just do this for any x. So we'll leave x as a variable. So rho equals the limit as n goes to infinity of the absolute value of, well, we're going to have a big fraction x to the n plus 1 power on top over n plus 1 factorial. And on bottom left, x to the n over n factorial. In this case, we have to keep the absolute value bars because, get this eventually, because x could be negative. X might be -1 or -2 or whatever. So we'll do a similar rearrangement of the fractions. So this is the limit as n goes to infinity of the absolute value of x to the n plus 1 power over n plus 1 factorial times n factorial over x to the n. Okay. So I'm going to do the same rewriting of n plus 1 factorial, and then also here in the numerator, I'll rewrite x to the n plus 1 as x times x to the n. So this is the limit. I'm almost out of room, I think. Yeah, almost. The limit as n goes to infinity of x times x to the n power over n plus 1 times n factorial times n factorial over x to the n plus 1. You can probably see where this is going. I get some cancellation. The n factorials go away. X to the n's go away. So this equals the limit as n goes to infinity of the absolute value of x over n plus 1. Now, n plus 1 is always positive, so I can rewrite this as the limit as n goes to infinity of the absolute value of x over n plus 1. And notice the active variable of the limit is n. So the limit sees x as being a number, not a variable. So this can move out in front of the limit. So this equals the absolute value of x times the limit as n goes to infinity of 1 over n plus 1, which is absolute value of x times 0, which is 0. So we get absolute convergence. Regardless of what n is. Okay, so this power series is convergent for any x value that we put in. So the terminology for this is radius convergence and interval convergence. That's detailed a little bit more on the next page there, but I'll go ahead and talk about it a little bit here. So since we get convergence for any x value, we're going to say that r equals infinity. The radius of convergence is infinite. And we'll say that the interval of convergence, the interval of the values for which, or rather the x values for which the series converges, is negative infinity to infinity. Okay, so let's get a little more detail on that. Given a power series of this form, a could be 0. One of the following is true, exactly 1. The series converges at a and diverges for all other values, which is not the situation that we had. The series converges for all x, which that is the situation we had in this first example here, okay? The third possibility is that there is some real number r between 0 and infinity such that the series converges if the absolute value of x minus a is less than r, so meaning that x is close to a, and diverges if the absolute value of x minus a is greater than r, meaning that x is far from a. The series may then converge or diverge at each x value where the absolute value of x minus a is equal to r. That's something you have to check individually. So, r is called the radius of convergence. In the first case, and by that I mean in this first case, not the example we had, but in this case, r is called 0. The radius is 0. And you don't really even have an interval because the radius is 0. In the second case, click back to zoom a little bit. In this case, r is infinity, which is what we had in the example that we did. In the third case, the interval is given by a minus r to a plus r, though possibly including the endpoints. And in this case, this is called the interval of convergence. Okay. So let's do some more examples of that. So let's find the radius and interval of convergence for this series. So because there's a factorial, I definitely want to use the ratio test again. And we're not going to bother choosing individual numbers yet. We're just going to start with any x. So rho equals the limit as n goes to infinity of the absolute value of n plus 1 factorial times x to the n plus 1 power all over n factorial times x to the n power. Okay. This equals the limit as n goes to infinity of, and I'm going to rewrite the numerator by doing some factoring. So n plus 1 times n factorial times x to the n, and on bottom we have n factorial times x to the n. And again, I'm keeping the absolute value of r's because x might be negative. So I get some cancellation, basically the same kind of cancellation we got earlier, and I'm left with the limit as n goes to infinity of the absolute value of n plus 1 times x. Now, n plus 1 is positive, so I can rewrite this as the limit as n goes to infinity of n plus 1 in parentheses times the absolute value of x. As before, the limit sees x as a number, so that absolute value can move out in front. So this is absolute value of x times the limit as n goes to infinity of n plus 1. Okay, now, if x is 0, then the series must converge because that's the center. In other words, you would have 0 times some limit that doesn't matter because you get 0 anyway, essentially. But you get convergence at 0 because that's the center. If x is anywhere else, well, then you're going to have some number times its limit, and that limit is infinity. So this equals infinity. So r equals 0. The radius of convergence is 0. We don't get convergence anywhere else. The rho is just infinity unless x is 0. So we also won't really refer to an interval of convergence because the radius is 0. So that's going to happen sometimes. That was the first bullet point where the radius is 0. So let's look at another example. So find the radius interval of convergence for the series as n goes from 0 to infinity of x minus 3 to the n power over n plus 1 times 2 to the n power. There's a couple ways to get started with this one, which it might help to rewrite this in the following way. This is not essential, but I think it might help. So I can rewrite this as 1 over n plus 1 times x minus 3 to the n over 2 to the n. In fact, let's do this. Save myself some room. And this equals the sum as n goes from 0 to infinity of 1 over n plus 1 times x minus 3 over 2 to the n power. Okay. So potentially we could use the root test, I suppose, because of with this exponent, but I think it would be better to use the ratio test again. So rho equals the limit as n goes to infinity of the absolute value of big fraction 1 over n plus 2 times x minus 3 over 2 to the n plus 1 power over 1 over n plus 1 times x minus 3 over 2 to the n power. Okay, so I think what would be the best thing to do to start would be to do some cancellation. Well, you know what? Let's do it this way. Let's do it this way. So let's do this. Let's write this as the limit as n goes to infinity of, yeah, let's do it this way first. There's several ways to do this. We basically have to do a bunch of algebra. Okay, so we get a bunch of cancellation here. Okay, then I'm going to do the step where I multiply the numerator by the reciprocal of the denominator. So this will equal the limit as n goes to infinity of the absolute value of 1 over n plus 2 times x minus 3 over 2 times n plus 1. Okay, as before, The ends are all positive, so I can rearrange this and just keep the x, the 3, and the 2 in the absolute value bars. So I can rewrite this as the limit as n goes to infinity of n plus 1 over n plus 2 times the absolute value of x minus 3 over 2. And again, this factor is seen as a number by the limit, so it can move out in front. So this equals the absolute value of x minus 3 over 2 times the limit as n goes to infinity of n plus 1 over n plus 2. Now, you might see what's going to happen next. This limit is 1, and we can cut corners a little bit and not bother showing all the steps, but basically, the 1 and the 2 don't affect the result, so you basically have n over n, which is 1, so the limit is 1. So this equals the absolute value of x minus 3 over 2. Now, the bottom's always positive, so I can write this as the absolute value of x minus 3 all over 2. So that's rho. Rho is the absolute value of x minus 3 over 2, whatever that happens to be. So depending on the x coordinate we choose, or x value, I should say. So if this is less than 1, then we get absolute convergence. If this is equal to 1, we don't get anything. We have to do a different test. If this is greater than 1, then we get divergence. So looking for convergence, essentially we're looking for the interval of convergence. We're going to set this less than 1 and solve. Okay, so we can multiply 2 on both sides. And there's two approaches to go from here. One way is to say, well, this is A and this is R. So my radius of convergence is 2. My interval of convergence is going to be, well, A minus R to A plus R, which in this case, A minus R, and notice that A is not negative 3, A is 3. Okay, from the format up here, x minus a is the part of the format. So if you had something like x plus 7, your a would be negative 7. Okay, so a is 3 and r is 2, so a minus r would be 1, and a plus r would be 5. There's an interval. Another way to do this is to solve this inequality by rewriting it as a 3-part inequality, like so, and then adding 3 to each component and getting your interval that way. Either one's totally fine. So we have our interval of convergence, except we have to check the endpoints. If rho equals 1, we get no conclusion. So we have to check those endpoints separately. So what if, how much room do I have? Okay. So if, say, rho equals 1, and that would happen when x equals 5. If x equals 5, okay, what do we get? Well, let's go copy this guy. Okay, if x equals 5, then this equals the sum is n goes from 0 to infinity of 1 over n plus 1 times, well, this will be 5 minus 3, so 2 over 2 to the n power. This is just 1. So this equals the sum is n goes from 0 to infinity of 1 over n plus 1. Which you might notice, you might be able to tell just from looking at it what happens. What we're going to do is, there's a couple of options. This series starts at 0. So here's what I'm going to do. I'm going to do a change of variable. In fact, I'm going to rewrite this here because there's a couple things we have to do. In most of the series tests we dealt with before, you start with n equals 1. So here's what I'm going to do. I'm going to say that m equals n plus 1 so that m minus 1 equals n. Okay? So, put this off to the side. So this equals, well, the sum as m, well, if n is 0, m is 1, right? And then n plus 1, well, that's m. Hey, that's the harmonic series. which we know diverges. Okay. I could have tried doing if I tried to do like a limit comparison test or a direct comparison test with the harmonic series, the problem is I'm starting at 0. With the harmonic series, you start at 1. So a change of variable is the better way to go, oh, this is the harmonic series. If you think about it, the sum as n goes from 0 to infinity of 1 over n plus 1. Well, if n is 0, this would be 1. If n is 1, this is 1/2. If n is 2, this is 1/3. And then 1/4 plus dot, dot, dot. Hey, that's the harmonic series, right? We don't need a test for that. We've already checked out the harmonic series. So this interval does not include the endpoint, okay? What about the other endpoint, if x equals 1? Well, let's duplicate this again. If x is 1, then this equals the sum as n goes from 0 to infinity of 1 over n plus 1 of, well, or times rather, well, if x is 1, this 1 minus 3, this is -2. So this is -1 to the n power. Oh, okay, so this is the sum as n goes from 0 to infinity of -1 to the n power times 1 over n plus 1. And you might see where this is going, but let's do the change of variable again. It's not the only way to do this, but it's one way. So again, m equals n plus 1. I guess I really didn't need up here. I thought we were going to use it, then we ended up not needing it. I thought we would need this. We ended up not needing it. So sometimes you might for a different change of variable, but in this case we didn't. So this is the sum as m goes from 1 to infinity, right? When n is 0, m is 1 of, this is where we needed it. Okay. M minus 1 equals n. So n is m minus 1. That's why I was thinking we would need it. It's this one, the other endpoint, not the first endpoint. Times 1 over m. You may recognize, hey, that's the alternating harmonic series. So this converges absolutely. Sorry, converges. Not absolutely. It converges. My mistake. So we get convergence at 1. So really, r equals 2 and I equals 1 to 5, including 1, but not including 5. So when you do this up here, you're checking for the 1 and the 5, but you're checking for the interval, but you have to test the endpoints separately. Okay. Basically, what you're doing is you're finding the interior of the interval, and then you check the endpoints afterward. Okay, so that's basically it. When you look for a radius of interval of convergence, you won't have to always use the ratio test, but it's typically the examples we're going to do here. The ratio test works for all of those. There might be an example in an assignment where you need a different test, but you should probably start with the ratio test. Because of the power series nature, you're always going to have something like this because you have a power series that we're talking about. So go for the ratio test by default. There might be cases where the root test is going to work better. Anyway, you do the ratio test, and then you check the endpoints. Okay, so let's do another example. So one way to consider the convergence of this series is to do a change of variable again, so it's more recognizable to something we've done before. So again, m equals n plus 1, so m minus 1 equals n. Okay, so the series as m goes from 1 to infinity of x to the m minus 1 power, which you might recognize, maybe not. Let's write this as the sum as m goes from 1 to infinity of 1 times x to the m minus 1 power. And this is getting closer to something we've done before, but let's go one step further. Let's say this is equal to the series as m goes from 1 to infinity of a times r to the m minus 1 power. Okay, this is a geometric series. And this converges to a over 1 minus r if the absolute value of r is less than 1. We've already worked that out ahead of time, so we don't need to use the ratio test and check the endpoints. We've already got that. So this series, this equals 1 over 1 minus x, provided the absolute value of x is less than 1. Or in other words, the radius of convergence is 1, and the interval of convergence is interval from -1 to 1, not including the endpoints. We don't have to go and check the endpoints because we already have this from identifying this with the geometric series. If you wanted to go confirm this with the ratio test, you could get that and then check the endpoints individually, but we don't need to do that since we've done that work already. So what we can say is, in the interval from -1 to 1, this series n equals 0 to infinity of x to the n, which equals 1 plus x squared plus x cubed plus dot dot dot. This equals 1 over 1 minus x. Okay, I'm just summarizing here. So we can represent this function using a power series. Okay, that's going to be very powerful for some topics in a later section. We'll do a few examples here as well. So let's look at a visual justification of this, just so it's a little more concrete. So I'm going to switch over. I have this graph set up, and I have y equals 1 over 1 minus x graphed in purple. And I guess I'll zoom in a bit, right? Now, I could put a restriction on this to only use the interval -1 to 1, okay? And you've got an asymptote there. So let's go ahead and do that. That's fine. So now, oh, I had already put it there. That's fine. And I guess I don't need that. So now I'm going to show this series going from 0 to big N, and right now big N is 0. So this is just one term. Basically, we're going to look at the partial sum. So if I turn this on, you'll see a line segment. This is y equals 1, basically. If I increase the number of terms, this is 1 plus x, okay? If I increase in terms again, this is 1 plus x squared. Do it again, this is 1 plus x cubed, and then 1 plus x squared plus x cubed plus x to the fourth. And if I increase this, you might notice that the left, this little bit here, kind of flops around, but the right, especially if I zoom out a little bit, you can see that on the right-hand side, this blue section, or this blue graph, is matching, or trying to match, the purple graph. And if I zoom in, you can see that here, the blue, at the end point, it doesn't quite match up, and here it does. So, basically, the power series is a good representation, good representation of that function. And if you only use a few terms, it's a poor representation. But if you use many terms, it's a very good representation. Basically, we're going to liken this to the linearization of a function. In a later section, we'll talk about having an approximation to any function that you want. Okay, let's switch back over to here. So that was some of the graphs of the graphs of some of the partial sums. So we're going to use a power series to represent this function, f of x equals 1 over 1 plus x cubed, and we're going to find the interval of convergence basing it upon the geometric series. So I can rewrite this as f of x equals 1 over, and I have 1 plus x cubed. I'm going to rewrite this as 1 minus negative x cubed. So this equals the sum, as n goes from 0 to infinity, of negative x cubed to the n power, as long as the absolute value of negative x cubed is less than 1. Okay, so absolute value of negative x cubed is less than 1. I can drop the minus sign, so x cubed less than 1. or in other words, the absolute value of x, that cubed is less than 1. And then I can apply the cube root function to both sides, so the absolute value of x is less than 1. So I find that r equals 1, and the interval of convergence is -1 to 1. And I don't need to check the endpoints because this is a geometric series. So this equals 1 plus -x cubed plus -x cubed squared plus -x cubed cubed. We'll do one more, -x cubed to the fourth plus dot dot dot. So this is 1 minus x cubed plus x to the sixth. The minus goes away because we have an even exponent on it. Minus x to the ninth plus x to the 12th. And then minus would be the next term, right? Dot dot dot. So this is a power series representation for this function on the interval -1 to 1. Okay? Let's do another one. So use a power series to represent f of x equals x squared over 4 minus x squared and find the interval of convergence. So I see a couple ways to get started with this one. So I'm going to write this as f of x equals, I'm going to write the x squared in front, and you'll see why in a moment, over, and I'm going to write this as 4 times 1 minus x squared over 4. Okay, so this equals x squared over 4 times 1 over 1 minus x over 2 squared. Okay, why did I do all that? Well, this has the format of 1 over 1 minus r, with r equals x over 2 squared. Okay, so this equals x squared over 4 times the sum, as n goes from 0 to infinity, of x over 2 squared to the nth power, okay? As long as the absolute value of x over 2 squared is less than 1. So we'll deal with the interval in a moment. I want to write out the power series representation for this. So this would be x squared over 4 times, well, 1 plus, I guess x squared over 4, I should write that, x squared over 4 to the first power plus x squared over 4 squared plus x squared over 4 cubed plus dot dot dot, probably enough. So I distribute this, I'll have x squared over 4, that's the first term, right? Plus x to the fourth over 16 plus x to the sixth over 64 plus x to the eighth over, I guess that's times 4 again, so 256 plus dot dot dot. Okay, I just realized that I could have done something a little bit different. So let's do this. Yeah, I have room, so let's do this here. I could have written this in the following way. Maybe this would have been easier, actually. Move that back inside. There we go. That's probably the easiest way to write the compacted version, but this is the sort of expanded version. So let's look for the interval of convergence. So the absolute value of x squared over 4 needs to be less than 1. Okay. Yeah. Okay. So this is, well, the absolute value bars we can just drop. Everything's positive anyway, or at least non-negative. So I can multiply 4 on both sides. So the x squared is less than 4, then x is between -2 and +2. So the radius of convergence is 2, and the interval of convergence is -2 to 2. And again, we don't have to check the endpoints individually because we have this is based upon a geometric series.